This is Numerical Integration Methods, my Calculus Module 2 presentation. The first method is Riemann sums. Here's the expression for the area from a to b between a function f of x and the x-axis. As Ted said in class, we are adding up the area of many small rectangles with width delta x, which is just b minus a over n, and height h of I, which represents the height of the rectangle at the ith step. This is all evaluated as n approaches infinity so that the rectangles can fit to the curve. For each variation of the Riemann sum, h of I is defined differently. The ones I have here are some of the common ones, although there are many more. For the left endpoint, the height of the rectangle is the left endpoint, as the name suggests, and it is similar for the right endpoint and the midpoint variations. For the trapezoid variation, we take the average of the left endpoint and right endpoints. Here are two images showing the left and right endpoint variations. And here are two images showing the midpoint and trapezoid variations. I implemented these four rules in Python and wrote a script to run the functions on increasing values of n. To test if it is correct or not, we can run it on a function that we know how to calculate the area of. From 0 to 1, the area between y equals x and the x-axis is just a triangle with base and height equal to 1. Thus, the area is 0.5, which agrees with our Riemann sum approximation. Running the simulation on more complex functions yields interesting results. On the right, you can see that the area under e to the x from 0 to 1 is around e minus 1. This makes sense because the antiderivative of e to the x is just e to the x, so to calculate the area normally, we would just take the difference of the indefinite integrals evaluated at the left and right bounds. On the left, we can see that the area from 0 to 1 between sine pi over x, the function that the design challenge was talking about, and the x-axis converges to around negative 0.2314. A note on this is that I could not use the left endpoint in trapezoid variations because I would run into a division by zero problem. The design challenge also asked about the geometric area, and to do that, we can just take the absolute value of all of the outputs of the function, which converges to around 0.6179. The last function that the design challenge talked about was sine squared pi over x, of which the area converges to approximately 0.4795. The second method is Monte Carlo integration, which is a method that is a lot more general than Riemann sums. The idea of this method is to plot random points in a defined area and see how many of them are in the area that we are looking for. This means that as the number of dots increases, we can expect the ratio of dots under the graph to the total number of dots to be approximately equal to the ratio of the area under the graph to the total area. To me, it makes sense intuitively why this should work, but how can we show that it works rigorously? Luckily, there's this thing called the law of large numbers, which I won't go into depth about, but essentially says that the average of a large number of independent samples from a probabilistic system approaches the quote-unquote true value, or the expected value. An example of this method, but not entirely equivalent to our integration process, is plotting points in a 2x2 grid and seeing how many of them are in the unit circle in order to approximate pi. In the first simulation on the left, we are plotting only 10 points. Since our sample size is very low, we are very far from pi, as shown by the percent error. In the simulation on the right, we plot 1,000 points. This drastically decreases our percent error. Plotting even more points, our percent error drops very low. In the right side simulations, where we pump up the number of points, something interesting arises. The percent error in the 1 million dots trial is less than the percent error in the 10 million dots trial. This is very important, and the reason that this comes up is that since all of these approximations are probabilistic, there is no guarantee that a trial with more dots will have more accuracy than one with less dots. Running the simulations on all the functions that we did before yields similar results. And same goes for the other two functions.